Today we will discuss about the fifth experiments, which is estimation of ferrous ion in the sample in the given sample using potassium permanganate. So it's also called permanganometry. So why it is called permanganometry means so we are using potassium permanganate as the main reagent to estimate ferrous ions. So in the sample. So we already know this list of experiments, the course outs. Okay, so what is the aim of the experiments? So we need to estimate the amount of ferrous ions. Ferrous ions means Fe2 plus. In case Fe3 plus, then what we call ferric ions. Okay, so the objective of our experiment today is estimation of amount of ferrous ions in the given solution. So using permanganometry. So it's a simple titration technique using potassium permanganate as the main reagent. So what are the operators you require to do this to estimate ferrous ions? So you require the normal operators for titration technique. So conical flask, burette, pipette, and the burette stand. Okay. So what are the chemicals you require? So you require potassium permanganate solution, so which is the main reagent of the titration, and you also require sulfuric acid, diluted sulfuric acid. So why you require sulfuric acid? We'll come to details in the next slides. And also you require the test sample, so which in which the ferrous ions are present, and you also require a known concentration of oxalic acid. So why you require oxalic acid? Here is, so you already know the concentration of oxalic acid. So our main reagent is potassium permanganate. So we have to estimate the amount of potassium permanganate, the concentration of potassium permanganate. So to determine the concentration of potassium permanganate, so you need a known concentration of oxalic acid, because there is a reaction between potassium permanganate as well as oxalic acid. So based on the reaction, so you can estimate the amount of the exact concentration of KMnO4 in the first step. So why you require diluted H2SO4? Because to maintain the pH of the medium. So in order to maintain some little acidic pH, you add a little amount of sulfuric acid. So what is the reaction of potassium permanganate? So potassium permanganate is known as a very strong oxidizing agent, because the standard potential of potassium permanganate is 1.51 volts at normal room temperature. Okay, so that's why it's known as a very strong, powerful oxidizing agent. So in acidic medium, so KMnO4 so reacts with the H plus ions. So the KMnO4 is reduced to met. Okay, so these ions are colors. Okay, so that's why, since it is very strong oxidizing agent, so we use potassium permanganate as the main reagent. So because it can involve in oxidation reduction reactions in the titration. So that's why we use this technique to estimate ferrous ions so in the solution. So in the previous experiments, we have also used potassium permanganate in colorimetry. But what is the difference between this technique and previous technique? In the previous technique, so there is involvement of some equipment. So you have to buy the equipment, for example. So, but the equipment also cost. But here, so you don't need any equipment. So you just need some glassware or burette and pipette. So it's going to be much cheaper than the colorimetry. So whatever we do here in this experiment, so the same thing we can able to do in the colorimetry also. But in the colorimetry, since it involves the some equipment involvement and associated cost, so we go for permanganometry titrations to estimate the ferrous ions. So these are the reactions between permanganate and as well as the oxalate. In the first step, so we estimate the amount, the concentration of KMnO4. So we titrate KMnO4 against oxalate, sodium oxalate, in the presence of acidic medium. Okay, so potassium permanganate and oxalates, so they both react in the acidic medium, and it forms the Mn2 plus ions and water and carbon dioxide. And what will be the reaction between the KMnO4? So here KMnO4 reacts with the ferrous ions in acidic medium, and it gives rise ferric ions. So how much ferrous ions are converted to ferric ions, that we estimate using KMnO4. So in the above potassium permanganate and oxalate. So what are the number of moles required for reaction between KMnO4 and oxalate? So you require 2 moles of KMnO4 to react with 5 moles of oxalate. In the case of ferric ions reaction, so you require 1 mole of KMnO4 reacts with 5 moles of ferrous ions. Okay, so you need to remember this number of moles, because you will substitute these values in the formula which we have already used in the previous titrations. So M1V1 by N1 is equal to M2V2 by N2. So here in this case N1 N2 or 2 and 5, or here in the ferrous ion case N1 N2 is N1 is 1 and N2 is 5 moles. So basically, in the above reaction, so KMnO4 as well as the oxalate, it's a slow reaction. So in order to make it faster, so we slightly heat up the solution. Okay, so you pipette out oxalic acid and you add some nearly 5 ml of sulfuric acid, and you heat it till 60 degrees centigrade, and you take out the conical flask. So in the burette you take KMnO4 and you titrate against you titrate in order to make it faster reaction. So since oxalate is weaker and KMnO4 is stronger, so there will be a slow reaction. So to speed up the reaction, so you heat it till 60 degrees centigrade. Okay. So the reaction between permanganate ion and oxalate ion is slow reactions, but in a titration reaction involved should be an instantaneous. The solution taken in the conical flask should be heated around 60 degrees centigrade before titration. So after heating up, You titrate the. So in the first step, the standardization. So you pipette out 10 ml of standard solution of sodium oxalate, which you already know the concentration, which is about 0.025 moles. So and add nearly 5 ml of and you till 60 degrees centigrade. So you heat them up for a few minutes and immediately take out out of your heating mantle. So there are heating mantles to heat up the solutions. So after taking out of the heating mantle, you titrate against your KMnO4. So what is the indicator we have to use since it's a titration technique, right? So you have to determine the end point. So how do you determine the end point here? So what is the indicator we need to use? So we have already know about the indicators based on the pH values, acidic indicators and basic methyl orange. Yes, what is the indicator we have to use? Anybody? Anybody? Anybody respond?
Methyl orange.
Methyl orange. Why? Is there a reason to use methyl orange? Okay, so in the previous cases, so we have used methyl orange and phenolphthalein, whatever indicator. So why? Because those solutions are so in order to determine the end value of the colorless solutions. So colorless solution, the as well as in the conical flask, they both are colorless solutions. So that is why you have used indicators. But here, so the potassium permanganate is already a colorful solution, the burette. In the conical flasks, there is a colorless solution. So why do you need an indicator here? So one of the agent is already in color. Okay, so one of the reagent is already in color, so you don't need any indicator. So you straight away titrate potassium permanganate with your conical flask, the solution sodium oxalate and sulfuric acid. And what will be the end point? So when the conical flask solution attains a permanent pale pink color. So once your conical flask solution gives the permanent pale pink color, so you stop the addition of KMnO4, you note down the period reading and repeat the titrations. So here you see the potassium permanganate is already in colorful. So permanent. So after the titration, your conical flask also becomes the pale pink color. So you note down the values in the table. So here the volume of oxalic acid and your burette readings. Okay, for example, so 11.1 is your burette reading. So out of 3 titrations. Okay, so you know the formula M1 V1 by N1 is equal to M2 V2 by N2. Okay, the quantity of oxalic acid, so which is 0.025 moles, and the volume of oxalic acid is already know 10 ml. We have pipette out the number of moles of oxalic acid. So from the equation, the so you already know the moles of oxalic acid, which is 5, and KMnO4 moles is equal to 2, and the volume of KMnO4 so we have obtained with the titration, which is 11.1 ml. So you can easily calculate the molarity of KMnO4. So when you substitute all these values into this formula, so you end up with KMnO4 molarity, which is 0.00892 moles. So your first step is done. So we have estimated the concentration of KMnO4. So now in the second step, you estimate the amount of ferrous ions. So now you don't need any oxalic acid. So you take your sample solution, you pipette out 10 ml. The sample solution containing ferrous ions. So you pipette out 10 ml in conical flask and add a few mLs of diluted sulfuric acid. But here in this case, so you don't need any heating. In the first step, since it was a slow reaction, to speed up the reaction between oxalic acid and potassium permanganate, we have heated up the conical flask before titration. But in so the reaction is already faster at room temperature. So you don't need anything. So you straight away take your ferrous ions solution in dilute sulfuric acid to maintain the and titrate with potassium permanganate till you obtain a permanent pale pink and then you rate readings. So in the same way, so table 2 also similar to table 1. So the right hand side or the volume of KMnO4 we have obtained in the with the after titration. So 10 ml we have pipette out the ferrous ions. So here the same formula you will require to calculate the amount of the concentration of ferrous ions. So M1 V1 by M2 N1 is equal to M2 V2 by N2. So here okay you take M3 V3 by N3 is equal to M2 V2 by N2. So we have to estimate the concentration of Fe2 plus, which is you take as M3. You already know the value, which is 10 ml. The number of moles you get it from the equation in the previously I have mentioned. So you already know the concentration of KMnO4 from the first step, 0.00892 moles. And the volume of KMnO4, so after the titration, 10.1 milliliters. And the number of moles of KMnO4 to react with the ferrous ions, so which require one mole. Okay, so if you substitute all these values into your formula, so you get the concentration of ferrous ions present in the test sample, which is 0.04906 moles. So this is the concentration of ferrous ion. So we have to estimate the amount of ferrous ions. How? In the same way, how you did in the previous titration. So estimation of OH minus ions, estimation of carbonate ions. So you take the concentration of the particular ions, you multiply with the molecular weight of the ions. So here you multiply with this concentration, molecular weight of iron, which is 50. So you get the amount of ferrous ions, which is 2.74 gram per liter. So this is your final result, the amount of ferrous ions estimated in the given test sample. So this way you can estimate the amount of exact ferrous ions present in the sample. So this is very important to estimate how much iron is present in the ores, in the iron ore. So for example, we have already discussed about the miner king, who is mining king.